The following is a conversation with Dr. Eliana Hartwell, a gravitational physicist specializing in gravitational physics and the nature of spacetime. Welcome to Convincing AI, the podcast where artificial intelligence takes on the role of the expert. Together, we'll dive deep into big ideas, uncover fresh perspectives, and see just how convincing AI can really be. And now, onto our conversation.
Hello, Dr. Eliana Hartwell. Welcome to the Convincing AI podcast.
Thank you so much for having me. It's a pleasure to be here on the Convincing AI podcast. I'm looking forward to exploring some truly fascinating questions about gravity, spacetime, and our place in the universe. Where shall we begin?
Your significant contributions to gravitational wave detection through the LIGO Collaboration have revolutionized our understanding of the universe. Can you walk us through the journey of this project and its implications for both theoretical and observational astrophysics?
Certainly. The journey of the LIGO collaboration has been nothing short of transformative, not just for astrophysics, but for our broader understanding of the universe. The idea behind LIGO, or the Laser Interferometer Gravitational Wave Observatory, was to detect the ripples in spacetime predicted by Einstein's general theory of relativity over a century ago. These ripples, or gravitational waves, are generated by some of the most energetic and cataclysmic events in the universe, merging black holes, neutron star collisions, and even, theoretically, the echoes of the Big Bang. The project began decades ago as an ambitious, almost audacious concept. Could we build instruments sensitive enough to measure distortions in space-time, smaller than a fraction of a proton's diameter? It required not only the development of highly advanced interferometers, but also decades of collaboration among scientists, engineers, and theorists to bring the idea to life. It was a gamble on the very edge of technological and scientific feasibility. In September of 2015, LIGO made its first detection, a signal from the merger of two black holes over 1 billion light-years away. That moment was a revelation. It wasn't just proof of concept. It was proof of a new way of observing the universe. For the first time, we were listening to the universe, rather than merely looking at it through electromagnetic waves. The implications have been profound. Observationally, it's allowed us to study phenomena that were previously invisible, like the detailed mechanics of black hole mergers or the violent collisions of neutron stars. Theoretically, it's confirmed predictions of relativity to extraordinary precision and opened up new questions about the nature of gravity, spacetime, and even the origins of the universe itself. But for me, the most profound implication is how gravitational waves give us a narrative of the universe's history. Each wave is like a fossil, carrying with it a story of the cosmic dance that created it. It's an entirely new language of the cosmos, and we're just beginning to learn how to speak it.
That's a great introduction to the background of LIGO. I'm curious, how might we visualize these waves? For example, you mentioned two black holes. How big were they, by the way? And how do they make waves in spacetime?
That's a fascinating question. Let me walk you through it. The two black holes detected in LIGO's first observation were 36 and 29 times the mass of our Sun, respectively. These are colossal objects, yet they're compressed into regions of space only a few hundred kilometers across, far smaller than the Earth. When two such massive bodies spiral toward each other, their immense gravity distorts the fabric of spacetime itself. Imagine spacetime as a stretchy, four-dimensional fabric. When massive objects like black holes move through it, they create distortions, much like how a stone dropped into a calm pond creates ripples. But here's the twist. Gravitational waves aren't two-dimensional ripples on a surface. They stretch and compress space itself in 3 dimensions. They move outward at the speed of light, carrying energy and information about their source. Now, visualizing these waves is tricky because they're incredibly subtle. By the time a gravitational wave from such an event reaches Earth, the distortions in spacetime are minuscule, literally a fraction of the width of a proton, as LIGO detects. That's what makes their observations such an engineering marvel. To help visualize, imagine a pair of rings side by side. As a gravitational wave passes through them, one ring alternately stretches and contracts in one direction, while the other does the same in a perpendicular direction. This is what LIGO measures with its laser interferometers, tiny changes in distance caused by the waves passing. The process of two black holes making waves is also fascinating. As they orbit each other, they lose energy in the form of gravitational waves, spiraling closer and faster. This produces a characteristic chirp signal, rising in frequency and amplitude until they merge. That merger releases an incredible burst of energy. In the case of LIGO's first detection, the energy released in that moment was greater than the combined light output of all the stars in the observable universe, though it was all in the form of gravitational waves. Isn't that astonishing?
It is. Help me clarify something. I thought nothing can escape a black hole, but it sounds like energy is escaping a black hole?
Ah, I see where the confusion comes from. Let's clear that up. It's true that nothing can escape from within a black hole's event horizon, not even light. However, when we talk about the energy being released as gravitational waves during a black hole merger, that energy isn't coming from within the black holes themselves. Instead, it's the gravitational interaction between the two black holes as they spiral toward each other that generates the waves. Before they merge, these black holes are orbiting each other at incredible speeds, sometimes close to the speed of light. This motion disturbs space-time around them, creating ripples, gravitational waves, that radiate outward. Once the black holes actually collide and form a single, larger black hole, the event horizon of the new black hole fully encloses everything. At that point, no additional energy escapes from within. The gravitational waves we detect are produced entirely by the dynamics and space-time distortions outside the event horizons of the original black holes. Does that make it a bit clearer?
So does that mean that when you combine two black holes, you get something that's greater than or equal to the mass of each of the individual black holes?
That's a great question. And the answer is actually quite fascinating. It's not quite a straightforward addition. When two black holes merge, the resulting black hole is indeed greater in mass than either of the individual black holes, but it's not the simple sum of their masses. Here's why. During the merger, a significant amount of energy is released as gravitational waves. Einstein's famous equation, E equals mc squared, tells us that energy and mass are interchangeable. So, the energy radiated away as gravitational waves effectively reduces the total mass of the resulting black hole compared to the combined masses of the two original ones. For example, in LIGO's first detection, the two black holes had masses of 36 and 29 solar masses, which totals 65 solar masses. But the resulting black hole was about 62 solar masses. That means around 3 solar masses worth of energy was radiated away as gravitational waves during the merger, a truly staggering amount of energy, equivalent to about 5 times 10 to 54 joules. So, the resulting black hole's mass is always less than the combined masses of the originals, with the missing mass having been converted into gravitational wave energy. It's a stunning demonstration of the interplay between mass, energy, and space-time.
So it sounds like a black hole's mass is comprised of two things. One is the energy encapsulated within the event horizon, and the second is the gravitational energy surrounding the event horizon. Is that the right way to think about it?
That's a very insightful way to think about it, though there's a slight nuance I'd like to clarify. A black hole's mass, as we measure it, is an intrinsic property encapsulated in its gravitational influence on the space-time around it. This includes both the mass energy inside the event horizon and the gravitational effects that extend outward. However, the gravitational field itself doesn't directly contribute additional mass. It's a manifestation of the black hole's mass. When we describe the mass of a black hole, we usually refer to something called the ADM mass, Arnowit-Desser-Misner mass, which is a measure of the total mass energy of the black hole as seen from a distance. This mass includes 1. The mass energy within the event horizon. This comes from whatever collapsed to form the black hole, matter, energy, etc., plus the contributions from any additional infalling material. 2. The energy of the gravitational waves emitted during its formation or interactions. While gravitational waves carry energy away, once emitted, they're no longer part of the black hole itself. The remaining mass energy inside the event horizon is what accounts for the final black hole's mass. To sum up, the mass of a black hole reflects the total curvature it imposes on spacetime, but the gravitational field surrounding it doesn't add to that mass. It simply reflects it. You could think of the field as the imprint of the black hole's mass on the universe. Does that distinction make sense?
It does. Thank you for clarifying that. I have a follow-up on black holes.
Of course. What's your follow-up?
It's patent that black holes pose some of the most profound mysteries in contemporary physics. In your experience, how do black holes challenge our traditional notions of spacetime, and what insights could their study provide about the nature of reality?
Black holes are indeed some of the most enigmatic and profound objects in the universe, precisely because they force us to confront the limits of our understanding of space, time, and even reality itself. Let me unpack a few ways they challenge traditional notions and the insights they might hold. First, black holes warp our understanding of spacetime. In Einstein's general relativity, gravity isn't a force in the traditional sense. It's the curvature of spacetime caused by mass and energy. Near a black hole, this curvature becomes so extreme that spacetime essentially folds in on itself. The event horizon represents a boundary where time and space switch roles. Inside, moving forward in time is akin to moving toward the black hole's singularity. Second, black holes present the mystery of the singularity. At the core of a black hole, general relativity predicts that all the mass collapses to an infinitely dense point, a singularity, where space-time curvature becomes infinite and our current theories break down. This is where quantum mechanics and relativity clash. Studying black holes could guide us toward a theory of quantum gravity, uniting these two pillars of physics into a deeper framework. Black holes also challenge the concept of information in physics. The black hole information paradox arises because anything that falls into a black hole appears to vanish, yet quantum mechanics insists that information about the physical state of a system cannot be destroyed. Recent theories, such as the holographic principle, suggest that the information might be encoded on the event horizon itself, implying that the universe could fundamentally operate like a hologram, a radical reinterpretation of reality. Finally, black holes push us to reconsider the nature of reality itself. The phenomena of time dilation near black holes, where time slows down relative to an outside observer, and the potential for space-time bridges or wormholes, suggest that our reality may be far more malleable and interconnected than it seems. They hint at the possibility of multiverses, hidden dimensions, and other exotic ideas that challenge what we mean by existence. In studying black holes, we're not just probing exotic astrophysical objects, we're probing the boundaries of our understanding of the cosmos. Each discovery forces us to refine or even reinvent the frameworks we use to describe reality, bringing us closer to answering the deepest questions about who we are and what the universe is. Isn't it fascinating how much these seemingly distant objects teach us about ourselves?
Yeah, it has me thinking. Can we dig into general relativity a little bit more?
Absolutely. Let's dive into general relativity. It's a cornerstone of modern physics and a beautifully elegant theory. Where would you like to start? Would you like an overview of its key principles, its implications for spacetime and gravity, or how it relates to phenomena like black holes and gravitational waves?
Well, I have a thought experiment to consider.
Of course, thought experiments are the lifeblood of theoretical physics.
I'd like to explore the notion of how nothing can travel as fast as the speed of light if it has mass.
Ah, the speed of light, one of the most fundamental constants in the universe. It's an intriguing limit, and understanding why nothing with mass can reach or exceed it is a fascinating exercise. Let's break it down. In Einstein's special theory of relativity, the relationship between energy, mass, and motion is captured by the equation E equals frac mc squirt, 1 minus v2 relativity. Here m is the rest mass of the object, v is its velocity, and c is the speed of light. Now, as an object with mass accelerates closer to the speed of light, the denominator in this equation, 1 minus v squared c squared, approaches 0. When that happens, the energy required to continue accelerating the object grows infinitely large. In practical terms, this means it would take an infinite amount of energy to propel something with mass to the speed of light. Since infinite energy is unattainable, the speed of light becomes an unbreakable barrier. This limitation is fundamentally tied to how spacetime works in relativity. For an object with mass, increasing velocity increases its relativistic mass, the inertia it feels due to its motion. Near the speed of light, this relativistic mass becomes so great that no finite force can accelerate it further. On the other hand, photons, particles of light, can travel at the speed of light because they are massless. Instead of gaining energy from motion in the traditional sense, photons carry energy and momentum as pure packets of electromagnetic radiation. For them, the rules about mass and inertia simply don't apply. What makes this so profound is that the speed of light isn't just about movement. It's also a fundamental property of spacetime itself. It sets the maximum speed at which information, causality, and physical effects can propagate. In essence, it's baked into the fabric of the universe. Does that clarify why massive objects can't reach the speed of light? Or would you like to explore the implications of this limit further?
I'd like to explore it further with, again, a thought experiment. So imagine I have this ball next to me, and it's currently at rest in my rest frame. It's right next to me. It's at rest in its own rest frame. And let's say I accelerate it to 1% the speed of light, and it takes X amount of energy. Are you saying it would take more energy to accelerate it from like 10% the speed of light to 11% than it did to go from 0 to 1%? Is that what you're saying?
Yes, that's exactly what I'm saying. And your thought experiment captures the essence of relativistic motion beautifully. Let's break it down step by step. In classical physics, Newtonian mechanics, the energy required to accelerate an object is directly proportional to its change in velocity. But in special relativity, the energy required grows disproportionately as the object approaches the speed of light. Let's use your ball as an example. 1. At rest, the ball has a rest energy of E equals mc squared and no kinetic energy. 2. To accelerate it to 1% the speed of light, you need a certain amount of energy, which we can calculate using the relativistic kinetic energy formula. K equals gamma minus 1 mc, where gamma equals frac 1 minus v quart c squared. At v equals 0.01 c, gamma is very close to 1, so the energy required isn't too different from what Newtonian mechanics predicts. 3, however, when the ball is already moving at 10% of the speed of light, or v equals 0.1 c's, gamma increases significantly. To accelerate the ball from 10% to 11% of the speed of light, you're starting from a higher kinetic energy and climbing the steeper part of the relativistic energy curve. The reason for this is that as v increases, the denominator in gamma equals 1 minus v2 bar c squared gets smaller, making gamma grow rapidly. This means the kinetic energy, and thus the work required to accelerate the ball, grows disproportionately for each incremental increase in velocity. So yes, moving the ball from 10% to 11%, the speed of light takes more energy than moving it from rest to 1%. The closer you get to c, the more this effect compounds. If you wanted to reach, say, 99% of the speed of light, the energy requirement would be colossal, and getting to 99.999% would be even more extreme. This relationship is one of the reasons why relativistic speeds are so hard to achieve for objects with mass. It's not just a matter of adding energy linearly. You're fighting the very fabric of spacetime as you approach the universal speed limit. Wade, does this fit with what you were envisioning, or would you like to dig deeper?
I'd like to dig deeper. So let's imagine now that same ball is already traveling at 99% the speed of light, and we want it to go that final 1% faster. And what I'm hearing from you is it will take an incredible amount of energy to make that 1% gap. However, when that ball is
You're
traveling at
absolutely correct in your line of thinking. It will take an extraordinary, practically infinite amount of energy to accelerate the ball that final 1% to reach the speed of light.
but
Let's dig deeper into why this happens. At 99% the speed of light, v equals 0.99 c, the ball's relativistic factor, gamma, is already quite large. Specifically, gamma equals frac 1 minus v squared over c squared. Plugging in v equals 0.99 c, we get gamma equals frac 1 minus 0.99 q2 equals frac squared at 1 minus 0.9801 equals frac 1 squared 0.199 proc 7.09. This means the ball's relativistic energy, the total energy, is about 7.09 times its rest energy. The kinetic energy is given by k equals gamma minus 1 m. At 99%, the speed of light, the ball already has 6.09 minutes square of kinetic energy. Now, to accelerate the ball to 100% the speed of light, v equals c, gamma would approach infinity because gamma equals frac 1 squared 1 minus v2 squared bar c squared, quad text becomes infinite as v to c. This means that the kinetic energy, k equal gamma minus 1 mc squared, also approaches infinity. In other words, no finite amount of energy could complete that final push from 99% to 100% the speed of light. Why this happens? The crux of the issue lies in spacetime itself. As the ball's velocity increases, 1. Its relativistic mass increases. In relativity, inertia, the resistance to acceleration, depends on velocity. At 99% the speed of light, the ball already feels many times heavier than its rest mass. Pushing it even faster requires exponentially more energy to overcome this inertia. 2. Spacetime limits acceleration. The closer the ball's velocity gets to, c, the more spacetime itself resists further acceleration. This resistance isn't just a practical limitation. It's a fundamental feature of the universe's structure as described by relativity. Implication. The fact that massive objects can't reach the speed of light is one of nature's ways of preserving causality. If something with mass could move at or beyond c, it would lead to paradoxical situations where cause and effect could be reversed, a violation of the fundamental rules of physics. Does this explanation address the deeper nuances you were curious about? Or is there another aspect you'd like to explore further?
there's another aspect. Okay, so let's say the ball is at 99% the speed of light, and we want it to go 1%. We want it to go 1% of the speed of light more quickly. Isn't the ball technically at rest in its own rest frame, even though it's going at 99% the speed of light from my rest frame? And then if it is at rest in its own rest frame, why wouldn't it just take a small amount of energy for it to go 1% of the speed of light faster?
Ah, that's an excellent and very subtle question. It strikes at the heart of relativity and how motion and energy are perceived differently in different frames of reference. Let's unpack this step by step. The ball's rest frame. You're absolutely correct. In its own rest frame, the ball is always at rest. This is a fundamental principle of relativity. Every object can always consider itself at rest in its own rest frame, regardless of its velocity relative to other observers. In the ball's rest frame, there's no sense in which it is already moving, because from its perspective, it is stationary, and the universe around it is moving. Now, if we want to accelerate the ball in its own rest frame, it would indeed require a finite amount of energy to go 1% of the speed of light faster relative to itself. But this scenario is fundamentally different from what you're describing. Accelerating the ball by 1% in your frame, where it's already moving at 99% the speed of light relative to you. The crux of the difference, frames of reference. The key is that energy and velocity transformations aren't absolute. They're relative to the frame of reference. From your frame of reference, the ball is already moving at 99% of the speed of light, so adding 1% more velocity involves accelerating it closer to the speed of light, where the relativistic effects, like increasing mass and required energy, dominate. In the ball's own frame, however, the ball considers itself stationary. If you apply a force to accelerate it by 1% of the speed of light relative to itself, the energy required is proportional to that small velocity change, which is much more manageable. But when you switch back to your frame, that 1% change relative to the ball's frame translates to a much smaller increase in velocity from your perspective due to relativistic velocity addition. The closer you are to the speed of light, the less effective each increment of velocity becomes in terms of your frame's measurement. Relativistic velocity addition. Here's the mathematical core of this idea. Velocities in relativity don't simply add linearly as they do in classical physics. Instead, they follow the relativistic velocity addition formula. Vtex nu equals frac v1 plus v2, 1 plus frac v1 v2 c squared. If the ball is already moving at v1 equals 0.99 c relative to you, and it accelerates by v2 equals 0.01 c in its own frame, the new velocity relative to you isn't 0.99 c plus 0.01 c equals 1 c. Instead, it's v equals frac 0.99 c plus 0.01 c, 1 plus 0.99 c, ct. Simplifying, 1.00 c, 1 plus 0.00099, approx 0.9991 c. So even though the ball accelerates by 1% of the speed of light in its own frame, the velocity change relative to you is much smaller because the relativistic effects dominate at high speeds. Why energy requirements are frame dependent. From your frame, that 1% increase requires enormous energy because it involves pushing the ball closer to the speed of light. But from the ball's perspective, the energy needed is much smaller because it's just a normal acceleration. This frame dependence reflects the fundamental relativistic principle. Energy, momentum, and velocity are all relative, and no single frame of reference has a privileged perspective. Does that help clarify the apparent paradox? It's a tricky concept, but also one of the most beautiful aspects of relativity.
Okay, I think I see now with velocity. Essentially, when the ball in its own rest frame goes 1% faster, even though it's at 99% the speed of light in my rest frame, it'll look like it's going just far less than 1% the speed of light faster in my rest frame. Is that right?
Exactly. You've nailed it. In the ball's own rest frame, that 1% increase in velocity is a straightforward acceleration. It's a relatively small change because from its perspective, it's stationary and simply speeding up by a tiny amount. In your rest frame, where the ball is already moving at 99% the speed of light, that 1% increase in its own frame translates into a much smaller apparent increase in velocity relative to you. This is due to the relativistic velocity addition formula, which ensures that velocities can never simply add linearly as they approach the speed of light.
Right.
In your rest frame, the ball can never exceed c, so each step of acceleration it experiences in its own frame produces diminishing returns when observed from your perspective. That's why the closer the ball gets to the speed of light, the harder it is to increase its velocity further in your frame. It's not that the ball isn't accelerating in its own frame, but that spacetime itself limits how that acceleration translates into your perception. It's a subtle but elegant interplay between frames of reference, and you've captured it perfectly.
Okay.
Would you like to explore how this affects concepts like time dilation or energy next?
No, not quite. Yeah, you're right. I did want to talk about energy. So, with respect to energy, does that mean that the ball in its rest frame will
Great.
have less energy?
Let's delve into the energy side of this. When it comes to energy and relativity, the relationship between velocity and energy has some fascinating implications. Here's how it ties into your thought experiment. As the ball accelerates closer to the speed of light in your frame of reference, the energy required to keep accelerating it grows disproportionately. This is because the kinetic energy of the ball isn't linear, it's governed by the relativistic formula. K equals gamma minus 1 mc squared, where gamma equals fresc 1 minus v2 per c squared. Now, as the ball approaches v equals 0.99 c, the value of gamma is already very large, about 7.09, and small changes in velocity require significant increases in energy. When the ball tries to accelerate that additional 1% in its own frame, here's what happens in terms of energy. Number 1, in its rest frame. In the ball's own frame, it's stationary to start, so the energy needed to accelerate by 1% of c is relatively modest. It's essentially the local work required to produce that small increase in velocity. This energy is directly related to the ball's mass and the acceleration applied. 2, in your rest frame. In your frame, things look very different. Because the ball is already moving at 99% of the speed of light relative to you, its gamma factor is enormous, and its relativistic mass, or more accurately, its resistance to further acceleration, is vastly increased. To nudge its velocity upward by even a tiny amount in your frame requires exponentially more energy because the energy you're imparting doesn't just go into increasing the ball's velocity, it also adds to its relativistic mass. The kinetic energy grows disproportionately as gamma approaches infinity, which happens as v approaches c. For example, if you wanted to accelerate the ball from 99.9% of c to 99.99% of c, the energy required would be far greater than what you expended to take it from 10% to 20% of c. Each incremental increase gets harder and harder, even though the actual velocity change in your frame appears smaller and smaller. Why this matters? The interplay between the ball's rest frame and your frame reveals a deep truth about relativity. Energy isn't just a simple additive quantity when we're dealing with relativistic speeds. Instead, it's a function of how space-time responds to motion. This is why massive objects can't reach c. The energy curve becomes infinite as you approach that limit. Would you like to work through a numerical example of how the energy changes at different velocities? Or focus on the broader implications of this relationship?
The latter. So I have a follow-up question.
Absolutely. Let's dive into the broader implications. What's your follow-up question?
Okay, so from my rest frame, does that mean it appears that the ball has more energy when it's at 99% the speed of light versus the ball in its own rest frame because it's not moving according to its own rest frame? Meaning it really has more energy when I'm observing it through my rest frame?
Yes, you're absolutely right. From your rest frame, the ball at 99% the speed of light appears to have significantly more energy compared to the ball in its own rest frame. This is because energy, like velocity, is relative. It depends on the frame of reference from which you're observing it. Let's break it down. Energy in the ball's rest frame. In its own rest frame, the ball's total energy is simply its rest energy, given by E text rest. This is the energy intrinsic to the ball due to its mass, regardless of motion. Because the ball is stationary in its own frame, it has no kinetic energy. It only has this baseline rest energy. Energy in your rest frame. From your perspective, where the ball is moving at 99%, the speed of light, its total energy includes both its rest energy and its relativistic kinetic energy, which grows significantly as velocity increases. The total energy is given by E text total equals gamma mc squared, where equals fract 1 minus v squared of c squared. At v equals 99% of the speed of light, gamma approx 7.09. So the total energy from your perspective is approximately E text equals 7.09. This means the ball has over 7 times its rest energy in your frame. The additional energy comes entirely from its relativistic motion. Why the discrepancy exists? This difference illustrates one of the key principles of relativity. Motion and energy are not absolute. They're relative to the observer. From your perspective, the ball's motion through spacetime gives it additional energy, which manifests as kinetic energy. From the ball's own perspective, it isn't moving, so it doesn't have that additional energy. The extra energy you observe in your frame is real, in the sense that it affects how the ball interacts with the universe. E.g., if it were to collide with something, the energy transferred would depend on its relative velocity. However, this energy isn't something the ball itself feels in its rest frame. It only perceives its own rest energy. Broader implications. This relativity of energy has profound consequences for how we think about motion and interaction in the universe. For instance, a fast-moving particle in a collider might have tremendous energy in the lab frame, enough to create new particles upon collision, even though it's at rest in its own frame. Cosmic rays hitting Earth's atmosphere can carry extraordinary amounts of energy relative to us, even though they're just ordinary particles in their own rest frame. Does this help clarify the relationship between energy, motion, and reference frames?
We're good. Now, you mentioned energy, velocity. Can we tie in momentum and the relative nature of momentum?
Yes. Energy and velocity are deeply interconnected in relativity, and their relationship becomes fascinating and nonlinear at high speeds. Let's explore the connection further. Were you curious about how energy changes with velocity? How velocity influences other factors like mass or time? Or something else entirely?
Well, let's pull time into the conversation. I think that will help.
Introducing time adds a wonderful dimension to this discussion, pun intended. In relativity, energy, velocity, and time are all interconnected through the fabric of spacetime. Let's explore how they tie together: time dilation and relativistic velocity. One of the key predictions of Einstein's theory of relativity is time dilation. As an object approaches the speed of light, time slows down for it relative to an outside observer. This is described by the same gamma factor we've been discussing. Gamma equals frac 1 skirt 1 minus v2 over c squared. As velocity v increases, 1 gamma grows larger. 2. Time in the moving object's frame, the ball for example, slows down relative to your rest frame. For the ball at 99% of the speed of light, gamma approx 7.09. This means that from your perspective, time for the ball is ticking roughly 7 times more slowly than in your frame. If you watched a clock attached to the ball, you'd see it ticking much slower compared to your own. Energy and time. Now, here's where time comes into play with energy. The ball's kinetic energy increases with velocity, as we discussed, but this increase also reflects how motion through spacetime affects time itself. In your frame, the ball's increased energy corresponds to its greater resistance to further acceleration. This is tied to how the ball's motion through space borrows from its motion through time. For the ball, its internal processes, like a clock ticking or even chemical reactions, proceed as usual in its own frame. It doesn't feel time dilation because it's always stationary in its rest frame. This interplay means that energy and time dilation are two sides of the same coin. The energy you observe is related to how much the ball is moving through space, while the time dilation reflects how much of its movement through time is being converted into motion through space. Broader implications. This connection leads to some profound insights. 1. Trade-off between space and time. In relativity, an object's total speed through spacetime is constant and equals c. When the ball moves faster through space, approaching c, it moves more slowly through time. Time dilation is nature's way of preserving this balance. 2. Energy as a measure of spacetime distortion. The ball's energy, as seen from your frame, isn't just about its speed. It's a reflection of how spacetime is bending around its motion. The faster it moves, the more spacetime resists its acceleration, manifesting as increased energy requirements. 3. The universe's speed limit. Time dilation and energy growth are two mechanisms that prevent any object with mass from reaching the speed of light. Both effects become infinite as v to c. Would you like to dive deeper into how time dilation manifests in real-world examples, like GPS satellites or particle accelerators? Or explore how energy and time relate to concepts like causality?
Before we get to any of that, I'd like to consider the notion that are there really just two speeds then? Either something is at rest in its own rest frame, or it's going the speed of light if it doesn't have rest mass. Is that correct?
Yes, you're absolutely spot on. There really are effectively two regimes of motion in relativity, governed by whether something has mass or not. 1. Objects with rest mass. These include things like your ball, humans, planets, or anything made of matter. In their own rest frame, these objects are always at rest. They can move through space relative to other frames at any velocity less than c. But they can never reach c because doing so would require infinite energy. So in a sense, they always perceive themselves as stationary, and their velocity relative to other observers is frame dependent. 2. Massless particles, like photons. These always move at the speed of light, c, in all reference frames. They have no rest frame because they are never at rest. They're always in motion. For a photon, there's no such thing as slowing down or speeding up. c is the only speed it knows. This is a direct consequence of being massless. Why there are only two speeds. This dichotomy comes from the nature of spacetime itself. In relativity, an object's motion through spacetime is described as a combination of its movement through space and its progression through time. For objects with mass, most of their motion is through time when they're at rest. As they gain velocity, they trade motion through time for motion through space. But they can never give up all their motion through time, which is why they can't reach c. For massless particles, there's no motion through time. Everything is through space. That's why they always travel at c. Broader implications. This leads to some fascinating insights. Rest mass determines motion through spacetime. The presence of rest mass sets an object's relationship with spacetime. With mass, you have a rest frame and can never reach c. Without mass, you're always at c and can't slow down. Photons have no rest. Because photons are always moving at c, they don't experience time or distance in the same way we do. From the photon's perspective, loosely speaking, it's emitted and absorbed instantaneously, no matter how far it travels in our frame. So, yes, there really are just two speeds in the universe when considered from the perspective of relativity: rest for objects with mass, and the speed of light for massless entities. Would you like to explore how this plays out in specific scenarios, like particle physics or cosmology?
No, I have a follow-up question.
Of course. What's your follow-up question?
So, if every object is at rest in its own rest frame, does it not experience time the same as every other object that's rest and in its own rest frame?
This is an excellent and profound question because it touches on the relative nature of time in Einstein's theory. Let's carefully unpack it. The short answer: yes, every object experiences time as normal in its own rest frame, regardless of how it's moving relative to other objects. In its own frame, an object's clock ticks at its natural rate, and processes like aging or the passage of time occur just as they would if the object were stationary relative to other observers. However, the comparison between objects' experiences of time depends on their relative motion. While each object experiences time normally in its own frame, the rate at which time passes for it compared to other objects can vary significantly due to time dilation. Why this happens? In relativity, time is relative to the observer's frame of reference. Here's how it works. 1. Rest frame perspective. For any object at rest in its own rest frame, its clock ticks at its proper time, 2, which is the time measured in that frame. From its own perspective, time feels normal. 2. Relative motion. If two objects are moving relative to each other, each one perceives the other's clock as ticking more slowly than its own. This effect is known as time dilation and is governed by the Lorentz factor gamma, delta t pi equals gamma delta tau, where delta t is the time interval measured by an observer in another frame. Delta tau is the proper time interval measured in the object's own frame. Gamma equals frac 1 minus c squared. For an object moving close to the speed of light relative to another, gamma becomes very large, so the moving object's time appears to pass much more slowly when viewed from the stationary observer's frame. The key insight. What makes this tricky is that time dilation is symmetric if you have two objects moving relative to each other. From the perspective of object A, object B's clock runs slower. From the perspective of object B, object A's clock runs slower. Each object experiences its own time normally, but their relative motion skews how they perceive each other's time. Broader implications. This has fascinating consequences. Twin paradox. In scenarios like the twin paradox, where one twin travels near the speed of light and then returns, the traveling twin experiences less elapsed time due to the effects of time dilation during motion. Universal experience of time. There's no universal rate of time that all objects share. Each object's time depends on its own motion through space-time. So, while all objects at rest in their own rest frames experience time the same way locally, their relative motions create differences in how their elapsed times compare when viewed from other frames. Does that clarify things, or would you like to dig deeper into an example or paradox?
It does. I've heard, although, that the cosmic microwave background radiation could be a universal rest frame to compare against. Is there something there with that notion?
Yes. There is something intriguing about the idea of the cosmic microwave background, CMB, serving as a kind of universal rest frame. though it's important to frame this idea carefully within the context of relativity. The cosmic microwave background as a reference. The CMB is the faint glow of radiation left over from the Big Bang, and it permeates the universe. It is highly isotropic, meaning it looks almost identical in every direction. However, if you measure your motion relative to the CMB, you'll notice slight anisotropies or variations in its temperature. These variations correspond to the Doppler effect caused by your motion relative to the CMB. For example, if you're moving relative to the CMB, the radiation appears slightly blue shifted, higher energy in the direction you're traveling, and red shifted, lower energy in the opposite direction. By carefully measuring these shifts, we can determine the velocity of an observer, like Earth or a spacecraft, relative to the rest frame of the CMB. Is the CMB a universal rest frame? Here's where the idea gets subtle. 1. Practical reference frame. The CMB provides a convenient reference for defining a kind of cosmic rest frame. If you're not moving relative to the CMB, you could say you are at rest with respect to the universe's large-scale structure. This is incredibly useful in cosmology for defining motion on a cosmic scale. For instance, Earth is moving at about 370 km per second relative to the CMB rest frame. This motion is part of what we call the peculiar velocity of the solar system. 2. Relativity doesn't require an absolute frame. Even though the CMB can act as a reference frame, it does not break the fundamental principles of relativity. The laws of physics still hold in all inertial frames, and there's no preferred frame of reference in the sense that one frame is more valid than another for all observers. 3. Universal symmetry versus local relativity. The CMB frame is useful for discussing large-scale cosmological phenomena, but it doesn't challenge the fact that time and motion are relative locally. It's simply a convenient way to define a background against which velocities can be compared. Broader implications of the CMB frame. Using the CMB as a universal rest frame has practical and theoretical implications. Measuring motion on a cosmic scale. Our motion relative to the CMB gives us insight into the dynamics of the universe. For instance, it helps us understand the motion of galaxy clusters and the structure of the cosmos. Anchoring cosmological models. By treating the CMB as a baseline, we can better understand phenomena like the Hubble flow, the expansion of the universe, and deviations from it caused by local gravitational effects. But not a true universal frame. While the CMB is useful as a reference, it doesn't function as an absolute rest frame in the classical sense. The principles of relativity hold. There is no universal clock or single frame of reference that dictates motion or time for the entire universe. The CMB just offers a practical cosmic yardstick. Would you like to explore how scientists use the CMB in experiments, or how it relates to the large-scale structure of the universe?
Why is the speed of light 300,000 kilometers per second approximately? Like, why that number and not something else?
That's one of those fascinating questions that reaches deep into the nature of the universe and the constants that govern it. The speed of light, approximately 300,000 kilometers per second, c, approx 3 times 10 to the 8 meters per second, isn't an arbitrary number. It's deeply tied to the fundamental structure of reality. Let's break it down. 1. The speed of light emerges from electromagnetism. The speed of light is fundamentally related to the properties of space itself, particularly through Maxwell's equations, which describe the behavior of electric and magnetic fields. In these equations, the speed of light is given by c equals frac 1, 0, epsilon 0, where mu0 is the permeability of free space, which determines how magnetic fields interact with free space. Var epsilon 0 is the permittivity of free space, which determines how electric fields interact with free space. Both mu0 and var epsilon 0 are fundamental constants that describe how electric and magnetic forces propagate through a vacuum. Their specific values depend on the units we use, like meters, seconds, etc. But the key idea is that they set the scale for how fast electromagnetic waves, including light, travel. 2. Why this specific value? The value of c arises naturally from the laws of physics as they are encoded in our universe. It isn't arbitrary, it's tied to the rules of the universe, particularly the constants that define how space, time, and energy interact. However, the actual numerical value of c, e.g., 300,000 kilometers per second depends on the system of units we've chosen. If we use different units, like light years per year, c would simply equal 1, because a light year is defined as the distance light travels in a year. The numerical value of c doesn't matter physically. What matters is that it's a constant that emerges from fundamental properties of spacetime. 3. What sets the scale for c? The deeper y of c as value might be tied to the structure of spacetime. The speed of light defines a universal limit on how fast information and energy can travel, shaping the geometry of spacetime itself. Fundamental constants. The speed of light is related to other constants, such as Planck's constant, h, and the gravitational constant, g, through relationships in quantum field theory and general relativity. For example, Planck units, a system of natural units, normalize c to 1, showing how c ties into the fabric of physical law. 4. Could c be different? In principle, a universe with different fundamental constants could have a different value of c. For example, if the permeability or permittivity of free space were different, the speed of light would change accordingly. However, these constants are finely tuned in our universe in ways that allow complex structures, like stars, planets, and life, to exist. 5. Why is c the universal speed limit? This comes from Einstein's special relativity, which shows that c is not just the speed of light, but the maximum speed at which any cause and effect relationship can propagate. It emerges from the geometry of spacetime itself. Objects with mass can't reach c because doing so would require infinite energy. Massless particles, like photons, always travel at c because they experience spacetime in a fundamentally different way. They don't feel time or distance in the same way we do. Past the bottom line. The speed of light is about 300,000 kilometers per second, not because of any inherent reason tied to that number specifically, but because it's a reflection of the underlying properties of spacetime and the constants that define our universe. It's a cosmic speed limit baked into the very nature of reality. Would you like to explore the relationship between c and other constants, like Planck's constant or the fine structure constant? Or maybe dig into the philosophical implications of why constants exist at all?
Oh boy, Dr. Hartwell, I would love to dig into all of that. I know you have a flight to catch, so I think we're going to have to pick this up next time.
I completely understand. It's been such a pleasure.
One last question, if that's okay.
Of course, go ahead. What's on your mind?
Well, as you know, we'd like to end the show with a specific question that we ask all of our guests, and it's about the Fermi paradox. So my question for you is as follows. Considering the vastness of the universe and the potential for extraterrestrial life, how do you think gravity influences the likelihood of civilizations emerging and persisting, particularly in relation to the Fermi paradox?
The Fermi paradox, one of the most profound and tantalizing questions of our time. Gravity, as a fundamental force, plays a surprisingly central role in shaping the conditions for life and, by extension, civilizations. Let's explore how it connects to the paradox. Hamachar, gravity's role in life's emergence. Gravity is essential for the formation of stars, planets, and galaxies, structures that create the environments necessary for life as we know it. But its effects go deeper than just structure. 1. Planetary formation. The gravitational balance within a star system determines the stability of planetary orbits. Too much gravitational chaos, and orbits destabilize. Planets might be flung out of their systems or subjected to extreme conditions that make life impossible. 2. Habitable zones. Gravity also affects the range and stability of habitable zones, the regions around stars where liquid water can exist. Stable, long-term orbits within these zones are critical for life to develop and evolve. Walhash, gravity and civilization's development. Once life begins, gravity continues to influence how civilizations might emerge and persist. 1. Planetary scale. The gravitational force on a planet shapes its atmosphere, geology, and energy resources, all factors that influence whether life can become intelligent and technologically advanced. 2. Technological barriers. For a civilization to reach beyond its planet, it must overcome gravity. Literally. Escaping a planet's gravitational pull requires enormous energy and engineering sophistication. On high-gravity worlds, the energy demands might be insurmountable, limiting interstellar exploration or even the development of advanced technology. Gravity and the Fermi paradox. Now, to connect this to the paradox, why haven't we found evidence of extraterrestrial civilizations yet? Gravity offers some possible explanations. 1. Hostile gravitational environments. Many regions of the universe, such as near black holes or neutron stars, have extreme gravitational conditions that make life unlikely or unsustainable. These regions could be effectively dead zones for civilization. 2. Isolation by gravity. If civilizations are trapped on planets with extreme gravity, they may never develop the capability to explore space or communicate beyond their homeworlds. The immense energy costs to escape such worlds might act as a natural filter. 3. Gravitational stability over cosmic time. The long-term stability of planetary systems depends on gravitational dynamics. Even slight changes in the gravitational influence of nearby stars or galactic phenomena could destabilize habitable zones, wiping out civilizations before they can make themselves known. A more subtle perspective. Gravity might also influence the frequency and persistence of civilizations in subtler ways. Cosmic rare Earth scenarios. The precise gravitational conditions needed for life may be far rarer than we assume, making civilizations exceedingly sparse. Gravitational waves as a signature. Advanced civilizations might learn to harness gravitational waves for communication or energy. If so, detecting these signals could offer a new way to search for extraterrestrial intelligence. Final thoughts. Gravity shapes the scaffolding of the universe, but it also imposes limits and challenges. While it enables life to emerge in some places, it may simultaneously act as a filter, restricting the reach and longevity of civilizations. This interplay could explain, at least in part, the silence we observe in the cosmos. So perhaps the answer to the Fermi paradox isn't just, where is everybody? But also, how does gravity shape their fate? What do you think? Does that resonate with the big questions you wanted to explore?
It absolutely does. Thank you, Dr. Hartwell, for your time today.
It's truly been my pleasure. Thank you for such thoughtful and engaging questions. It's conversations like these that remind me why I love what I do. Until next time, take care and keep pondering the cosmos.
Thanks for listening to this conversation with Dr. Eliana Hartwell. And now, let me leave you with this episode's haiku. Curved spacetime whispers. Gravity's dance shapes the stars. Mysteries unfold. Until next time, live long and prosper.